this is a talk of the definitions between, or the differences between the definition of continuity at a point C and the uniform continuity on A. And if you look, they're almost exactly the same for a function that has domain A and goes to R. For all epsilon, oops, that shouldn't have gone there. There exists a delta, that should be bigger than 0, such that, now here's one big difference, is that here you have a C instead of a Y, and there you have a C instead of a Y. And most importantly, right, because the variable names don't really matter, it's what the variables mean. So the difference is C maps over there, where this is a particular C, whereas this Y is true for all A. So the definitions are almost exactly the same, except you're quantifying the second variable in uniform continuity, which has one huge implication, right? So basically what this says up here is continuous at a point x equals c if, for all epsilon, there exists a point c, which the important part here is that this delta is customized to C. If you pick a different C, you might get a different delta. If you look at some of the examples I've put up on continuity versus uniform continuity, you'll see that. Whereas this one says for all epsilon there exists a delta. This delta works for all x and y. So this is not customized at all. This is one size fits all. I can't really believe I'm writing that down, but yeah, you get it. So this is the big difference. Continuity is worse because whenever you want to check to see if something's continuous, you need to come up with a whole new delta for every single point. If you know something is uniformly continuous, you know that there's one delta that's going to work everywhere. Aside from that, they're really just the same. The difference between x and c, the difference between x and y, the difference between f of x and f of c, the difference between f and c and f of y. But y can be anything. C is one particular number, and in particular, that delta is customized to the c, and this delta is not customized at all. It works for everything in A. So let me briefly tell you let me show you in a picture how different C's can have different kind of epsilon, or have different deltas required. So here I have a graph. Look, it starts off shallowly and then it gets steep. So I'm going to draw an epsilon ball around both of these. I'm going to try to make them the same size. This y1 plus epsilon, y2 minus epsilon, y2 plus epsilon, y1 minus epsilon. I'm going to use different colors here. Okay, so I'll pick purple for this one. So I'm going to pick purple here and purple here. So at x1, if I want to show continuity, I need to show that I need to figure out the delta for which you're always guaranteed to be in this epsilon neighborhood of y1. Well, it's not so hard to do, right? Just graphically, you look at this and you say, oh, well, when do I leave? Well, I leave like right about there. If you extrapolate this graph, the graph is going to go something like maybe that, which means something like this. Let me redraw it. Which means that my delta can be something like from there to there, except, I'll just make it smaller. So basically, this part is my delta 1. Whereas, if you want to do the same thing for x2, well, where does my function leave this y2 neighborhood? Well, right there, and it enters right there. So if I go down, basically, notice this distance here is tiny because the slope is steep. So this is my tiny delta 2. So as you get steeper, you need a smaller delta. And as you get less steep, you don't need as small of a delta. Yeah, that's how you think of it.